Okay, this was our endotracheal tube improvements and cheaper training dummy project. So for our problem, catheters for endotracheal tubes are made of latex, and this creates a great difficulty for patients with latex allergies, as we cannot use a latex catheter on them. Catheters also don't protect the most fragile part of the tube, and finally, training models are very expensive. So the current solution slash the procedure for this is that a catheter guides the tube through the nose and nasopharyngeal space. But if someone is allergic to latex, the endotracheal tube is pushed in the nose without the aid of a catheter. These This can cause complications such as broken bones, bleeding, and further deformation of organs. So for initial ideas, first we were to replace latex with a substitute material with similar properties. Our second idea was just to improve the design and add additional flair to the end, which protects the cuff of the catheter. Finally, integrate into the endotracheal tube. This would be integrating the catheter into the endotracheal and creating it as one tube. Our initial design is that concept one is the lowest level of design, meeting the bare minimum requirements of a catheter, just not made of latex. Concept two is our final design, as later described, and concept three is a group of three concepts that we were considering as additional parts if we had time. An extra, less necessary addition the hospital had noted to be helpful was to add a light to the end of the catheter to make guiding the catheter easier. This is our decision matrix. Our final decision was to improve the current design without latex. From our decision matrix, this had the highest value. This solution would help those with latex allergies while also helping children be intubated. The problem with other designs is that replacing latex didn't improve the current design enough, and integrating the catheter into the endotracheal tube can lead to interference with the gag reflex. So our final idea slash solution was to make a catheter with a second increase in diameter and length to protect the cuff, make a catheter using a similarly elastic, flexible, and smooth material to latex, most likely silicone or polyurethane. Use a 3D printer to create models of the trachea, nasal cartilage, and create membranes in the nasopharyngeal space using cardboard, and attach them all to a skull, and a significantly cheaper model is made. For research, design document received from the hospital detailing specific issues and requirements. We got resources for models of human body parts found through paper detailing 3D printed human body models. Multiple interviews with Dr. Sean Edwards to find out more specific requirements of model positioning of organs and soft tissue, and specifics on how to get the endotracheal tube and how it's used. We ordered catheters and endotracheal tubes to get dimensions for parts and CAD. For our research, again, we researched different materials for resins and synthetic rubbers that fit the basic requirements we set. The requirements were softness, smoothness, elasticity, and non-latex material. Final materials were polyurethane, synthetic rubber, silicone resin, and nitrile synthetic rubber. Those images say or list their specifications. For design process, we first thought about creating a training dummy. We started with a pre-bought skull, added pieces of paper to signify locations of soft tissue, and we would later replace these pieces of paper with specifically designed 3D prints and cardboard. We also, the main part of our project was to create a catheter that had a cuff that increased the protection. We noticed that something with a wide diameter can develop, and decided on adding a wide flare to the cuff. For our final design, we have a replication of the original catheter with an additional flare added to the end with wider diameter that can accommodate the cuff and protect it. The dummy is skull with prints of nasal cartilage and larynx directly attached to it, positioned in approximations of where they would be in a normal real human. The membranes are also very broad approximations. This is our CAD. In the top left, you have the base catheter design. The bottom left, you have a catheter that's split into thirds for printing on smaller beds. We later didn't do this because we found out that our material that we were printing out of was not good with glue, and it was not going to be efficient to have them in separate parts. Because of that, on the top right, we coiled it to make sure it would fit in the printing space, and the bottom right is a mold of the catheter. Here on the left side, we have the nasal cartilage, and on the right, we have the trachea, larynx, hyoid bone, and the thyroid model. For our 3D prints, the larynx and nasal cartilage printed using ABS on Stratus's F12 printer, and the catheter printed on Form 2 SLA printer with elastic 50A resin, and cured and washed using FormCure and FormWash post-processing. On the left, we have essentially the throat, the larynx, and it's reinforced by wood. In the middle, we have the full catheter, and on the right, we have the catheter coiled, and then the nose in the bottom right. For assembly, the membranes taped on using masking tape, the nasal cartilage secured with hot glue, tracheal model secured to the floor of the mouth with hot glue, and the thyrohyoid space reinforced with wood. Testing, we did quite a few tests, but the main ones were that we used paper model membranes, but they were too flimsy, and we replaced them with cardboard. We had to replace the trachea because the first broke very early, and we interviewed Dr. Sean Edwards regarding catheter materials and showed samples of all of them. Based on the doctor's advice, we went to the silicon resin that was shipped by Formlabs. For results, we did many interviews and determined the elastic resin was most effective. We determined that the lower layer height on the trachea strengthened print. Adding small wooden beams across the thyrohyoid space strengthened the trachea further. Cardboard for soft membranes held up much better, and elastic 58 resin decided upon as material for printing. For the value proposition, the previous known costs that we know is that authorized intubation training dummies cost at least $3,000 at the lowest, and intubation catheters cost around $3 to $15 individually. With lubrication annual cost is around $5,460. For our estimated cost for a product, our test dummy would cost around $100, and assuming mass production of our catheters would cost approximately $20 individually, primarily because they're more specialized. For market potential and originality, non-latex catheters of the required size don't exist for purchase, and these specific catheters with cuffs don't exist for purchase, so the product is very profitable. 3D printed dummies exist, however, the design lacks reproducibility. Finally, affordable skull dummies like this don't exist, so the product holds even more value in the market. For social impact and social value and global impact, assuming it is perfected and shipped globally, this has a huge impact in the field of medicine. For one, latex-free intubation solves the problem of people with latex allergies not being able to be intubated with the catheters. It can also intubate children easier because the cuff adds a second layer of protection for the children's nose and nasal cavity. This can also possibly reduce costs for catheters made for intubation, and it drastically reduces the cost of training how to intubate because the skull dummy is so much cheaper. There's sources.